Hi class, welcome to exercise 1J, simultaneous equations using substitution. In this lesson, we're going to put together all that we know about linear relations to learn about simultaneous equations. These are important skill in mathematics for both number problems and real-world applications. So before we begin, it's important that you're already very confident with all the algebra methods we've used and all other things that relate to linear relations, especially how a solution pair for a linear relation has an x and a y value and all that is involved with parallel lines. Okay, so let's have a look at the examples and pre-learning for this exercise. First, we'll have example 27, where we'll be solving simultaneous equations using substitution. And your questions that relate to this example are questions 1 and 2 in the new book and question 4 in the old book. Then we'll move on to example 28, where we'll be solving with both equations of the form y equals mx plus c. And your questions relating to this example are questions 3 and 4 in the new book and question 5 in the old book. Okay, let's move on to the introduction. If I were to give you a linear relation, how many possible solutions would there be? Hopefully you said infinite. For a real-world example, we could say Bob's car rental firm charges $60, then $20 per 100 kilometres after that. When they calculate their price, they'd use a linear relationship, where P for price will equal 60 plus K for kilometres, multiplied by 1/5, because 20 per 100 is the same as saying 1/5. When I say there's infinite solutions, I mean there's a price for 1 kilometre, P will equal 60.2. So 60.2 is a solution. If we travelled 200 kilometres, then P would equal 100. So 200, 100 is a solution. I can also find a solution to how many kilometres I could travel on a particular budget. So for example, if I had $150 to spend, then I could travel 450 kilometres. So 450, 150 is a solution. We could keep going with this, but we don't have infinite time to go through all the possible solutions. Okay, let's say there's another car rental company called Neil's Car Rental, and they charge $150 plus $10 per 100 kilometres. Now, using the same variables with P as price and K for kilometre, we could write this as P is equal to 150 plus 1/10 times K. Of course, there are infinite possible solutions where I could find the price to travel for any positive amount of kilometres, or I could figure out the amount of kilometres to travel for any price over 150. But we've already been through that regards Bob's car rental. However, now I'm going to look at comparing prices between companies. So while I travel around Melbourne, I travel for less than 200 kilometres normally. So it'd be cheaper to use Bob's car rental because, as we saw, the cost for Bob's car rental would be 100 over 200 kilometres. And if we were to figure out Neil's, we could see it would cost us $170. Sometimes I travel up to Brisbane and back, which is around 3,000 kilometres. And when I do this, it is cheaper to use Neil's because, using the 3,000 kilometre example, Bob's car rental will cost me $660, whereas Neil's will cost me $450. However, sometimes I do return trips to Victorian country towns, and that can be anywhere between 300 and 1,200 kilometres. Obviously, Bob's company is cheaper for the shorter trips and Neil's is better for the longer trips. And it gets confusing to decide which company to choose sometimes. So what I'd like to do is find out how many kilometres travel it is for the companies to charge the same price. In other words, when is K and P the same in both equations? That way I can make up my mind which company to use by knowing the distance. And if I need to travel more than this equal price distance, I will use Neil's company. And if it's less, I'll use Bob's company. And to make this problem a little simpler, I'm going to use variables that are more common to us. So price will equal Y and kilometres will equal X. We could begin our search by making tables of these values for X values of 400, 800 and 1200. Then when Y equals 1/5 of X plus 60, then for these corresponding X values, we have 140, 220 and 300. And when y equals a tenth of x plus 150, our corresponding y values are 190, 230, and 270. And let's close this off so it looks like a table. So when it's 800 kilometres, we can see the price is better for Bob's. And when it's 1200 kilometres, we can see the price is better for Neil's. So the solution must be somewhere between 800 and 1200, which will be a little bit easier to see on a graph. So here's something I cooked up a little earlier, which will allow us to mark in the points from our table, which were for Bob's 140, 220, and 300. And for Neil's, it was 190, 230, and 270. Of course, these are all related to x values of 400, 800, and 1200. Now, because these are linear relations, which conveniently is the name of the unit you're studying, we know we can graph these as straight lines. Now, by drawing these lines, we can see they tend to intersect here, which appears to have an x value of 900, and the intersection means that they'll have an equal y value as well. So let's check the equations. For Bob's, we have y equals 1/5 of 900 plus 60, which is equal to 240. And for Neil's, we have y equals a tenth of 900 plus 150, which equals 240. So they're both the same. Therefore, that point is definitely 900, 240. So while it's really exciting there that we could see that we could find the solution going through a table one at a time, drawing graphs, finding their intersection, it is fairly time consuming. And like all smart people, I'm guessing you want to learn the algebra shortcut. And in this sort of situation, for a shortcut, we use what's called simultaneous equations. In this class, we're going to learn a method called substitution, but there is another method, which we'll learn in the next lesson. We've seen that there's infinite solutions to a relationship between two or more variables, which is basically every possible pair on a line. However, we know that there's only one solution to a linear equation with one variable. So the trick to this method is using one equation to reduce the other to a single variable. So using the example we've already been working with, we begin by writing out both of these relations and numbering them. And we'll call Bob's 1 and Neil's 2. Then we should realise that if we're going to satisfy both of these equations, then y must equal 1/10 of x plus 150 in both of them. So we can substitute that y into the first equation. So now we have the equation 1/10 of x plus 150 equals 1/5 of x plus 60. And clearly x is our only variable in the equation now, so we can solve for that. And we end up x is equal to 900, just like our other solutions. So that means to satisfy both of the equations, we need to have a value of x equals 900. To find out what the value of y is, we only need to substitute this value of x into either equation to find the value of y. In this case, we'd sub in the 900 for x, and we demonstrated we'd get the same y. However, we've already done that. If we look back up at our graph, so here you can see that when x is equal to 900, y is equal to 240. Isn't that exciting? Phew, it's glad to know that maths is not broken. So we've seen there's infinite solutions for a linear relation between two variables. We've also seen there's one solution for a linear equation with one variable. So the question for you is, how many possible solutions are there that satisfy two linear relationships? Now, because we can represent linear relations as a graph, and we can describe the solution that satisfies both of them as the intersection of these graphs, we can use what we already know about the graphs of linear relations to answer this question. So if these linear relations form parallel lines, then we have two possible situations, which is either they never intersect and the simultaneous equations will have no solutions, or the two relations make the same line, which ends up having infinite solutions, which is practically the same as saying there are no solutions. On the other hand, if they're not parallel lines, then there's exactly one solution. Okay, let's move to the next section where we get to put these into practice. If If you're asked to simultaneously solve two linear relations by substitution, then you make sure that one of them is of the form y equals mx plus c. Then you can substitute mx plus c for y into the other relation. Also, just note that we normally substitute for y, but you could easily do this for x if you want to. It's not that crazy. Anyhow, let's put this knowledge and these skills into practice and do example 27, where we're asked to solve the following simultaneous equations using the substitution method. Okay, in part A, we have 2x plus y equals minus 7, which we'll name as equation 1. And y equals x plus 2, which we'll name as equation 2. So clearly equation 2 is of the form y equals mx plus c. So let's substitute our x plus 2 in the place of y for equation 1, which now becomes 2x plus x plus 2 equals minus 7. And when we collect like terms, that's 3x plus 2 equals minus 7, or 3x equals minus 9, and we finally get x equals minus 3. So let's sub x equals minus 3 into equation 2, and we now get y equals minus 3 plus 2, which means y must be equal to 1. And therefore we write out our solution nicely as the solution is x equals minus 3 and y equals minus 1. Now let's look at that on a graph. So I'll start by drawing some axes and mark in some x values, starting with the positive numbers and the positive values of y and the negative values of y. And I'm going to use the intercept method here to mark these graphs. So when relation 1 has a y value of 0, x will equal minus 7 on 2, which is 3.5. And when x is 0, y is equal to minus 7. So let's draw a straight line between those two. And for relation 2, when x is 0, y is equal to 2. And when y is 0, x is equal to minus 2. And let's draw a straight line between those two. And we can see their intersection here that has an x value of 3 and a y value of minus 1. So the point of intersection is minus 3 minus 1, just as we found as we've solved the simultaneous equations by substitution. Okay, let's move on to part B, where we have a relation 2x minus 3y equals minus 8, and we'll name that relation 1. And another relation y equals x plus 3, which we'll name relation 2. So if we substitute relation 2 into 1, we get 2x minus 3 times x plus 3 equals minus 8, with x plus 3 replacing the value of y. So if I expand these brackets, I now get 2x minus 3x minus 9 equals minus 8. And then by collecting like terms and adding 9 to both sides, we end up with minus x equals 1. So we know now that x will have to equal minus 1. And if we sub x equals minus 1 into relation 2, we end up with y is equal to minus 1 plus 3. In other words, y is equal to 2. So our solution is x equals minus 1 and y equals 2. And let me very quickly draw this graph, once again using the intercept method. And for relation 1, our y-intercept is when x equals 0. So that is 8 on 3, which is nearly 3. And our x-intercept is where y equals 0, so that is minus 4. And for our second relation, when x is 0, y is equal to 3. And when y is 0, x is equal to minus 3. So let me join up these lines, which isn't perfect here because I haven't drawn the graph perfectly. So let me fix up 8 on 3. And that's much better. We can see that the intersection here is where y is equal to 2 and x is equal to minus 1. So our solution is definitely x equals minus 1 and y is equal to 2. So I think it's pretty cool that our algebra follows what we can see on a graph. However, you do need to practice using this algebra. So at this point, I suggest that you pause the video, and then if you're working with the new book, you need to do questions 1 and 2. And if you're working with the old book, you need to do questions 4. and then I'll see you in the next section. So when we solve simultaneous equations, when we have two equations of the form y equals mx plus c, there really is no choice. You must substitute for y, which is pretty much what we've already been doing anyhow. So we'll just get on with the example, but I'd also like to mention at the end of this example, I do have a OneNote treat for you. So in example 28, they ask us just to solve this one simultaneous equation. With the first equation, y equals minus 3x plus 2. And the second equation, y equals 7x minus 8. So in this case, it's hard to say if I'm subbing 2 into 1 or 1 into 2. But really, I suppose I'm subbing 2 into 1 here if I write 7x minus 8 equals 3x plus 2. Then by collecting like terms, I'll get 10x, and adding 8 to both sides, I get 10. So we end up with 10x equals 10. And therefore x must equal 1. So if I sub x equals 1 into equation 1, we end up with y equals minus 3 times 1 for the x plus 2. And minus 3 plus 2 is minus 1, so we end up with y equals minus 1. So the solution is x equals 1 and y equals minus 1. Okay, so what is this OneNote treat? Well, let me write out these equations again. And notice how I've written x. For some reason, when I write x in the curly way, it doesn't recognize it. Okay, so next I'm going to highlight these and select maths. So we can see that at this point, OneNote's recognizing my comma as a 7. So I'm going to fix that. And now it recognizes it as two equations separated by a comma. So this is how a computer would know to do something like a simultaneous equation or graph two equations. So remembering that our solution is x equals 1 and y equals minus 1, let's have a look at what OneNote gives us. So let's plot that and have a look. So clearly this purple line here is our first equation, and this light pinky line is our second equation. You can check the intercepts with this yourself. And we could insert this graph on the page. And clearly the intersection is x equals 1 and y equals minus 1. But if you want to go one step further, you can choose this solve for y and x. And when you choose show steps, you can choose between elimination or substitution is a method we've learnt today. If you click that book and speaker icon, it'll read it out to you, or you can drag it onto the page. And there you go, there's all the solutions. And at the bottom you can see y equals minus 1 and x equals 1. So we have confirmation, the computer agrees with us. Having said that, you're going to need to practice this yourself because you won't be able to use this OneNote in a test. So at this point you should pause the video and work on question 3 if you have the new book, or question 5 if you have the old book. And when you finish that, we'll summarize our lesson. Okay, so that's it for this lesson. In our next lesson, we'll be learning another method to solve simultaneous equations. Both are very useful, but it's also important that you work really hard to understand this substitution method. When you finish this lesson and the pre-learning for it, you can consider this lesson a success if you're able to understand that a single linear equation in two variables has infinite number of solutions. Know that two simultaneous linear equations can have 0 or 1 solution. Understand that the solution of two simultaneous equations satisfies both equations and lies on both straight lines. Know how to substitute one algebraic expression for another to obtain an equation with one unknown. And if you can put these all together, you'll be able to solve simultaneous equations using the substitution method. And those of you who can confidently tick those off will be able to come to class and cover problem solving, because it can be really tricky sometimes to understand how a real-world problem can be expressed as a linear relation. This will be covered in detail in the final lesson of this block. However, as this is both the most difficult aspect of simultaneous equations and the point of learning them, it is important that you're using this lesson as well to build towards that. And reasoning, so you'll get the chance to build some real confidence with the concepts behind the substitution method for simultaneous equations. Okay, let's keep up the great work and I'll see you in class or the next video. Bye.